morning, professors. Today's presentation is going to be about synthetic word embeddings for downstream NLP applications. So let's walk through the overview of the presentation today. The objective: design a system for a given unknown word and synthesize an embedding that is semantically similar to that unknown word. We'll be reviewing existing approaches, what are the existing ways that can tackle the problem of unknown words in NLP model, and using the insights from these existing approaches to develop a fast and extensible framework to synthesize embedding for an unknown word. So this is the table content. We'll be walking through the introduction, existing approaches, system design, experiments and results, extension to Robota, and future work and conclusion. So let's start with the introduction. So synthetic word embeddings. In order to understand, we must first recap on what is a word embedding. Word embedding is a representation of words in the form of a real-valued vector that encodes the meaning of the word. Words that are closer in this vector space are expected to be similar in meaning. So let's review the progress timeline of how word embedding has progressed over time. In 1988, it first appeared as latent semantic analysis, also known as LSA. In 2003, Blay, Andrew Ng, and Michael Jordan formed the probabilistic latent derivative allocation in machine learning, which is PLDA. In 2013, the work of Thomas Mikolov in distributional semantics has revolutionized the field, and word2vec became a very popular word embedding of choice. And most recently, in 2018, the contextual representation, which is popularized by the work of Devlin in his transformer network, really has revolutionized the field in embedding. So why is word embeddings important? Word embedding is how NLP model encode human text and is the input to most tasks. Relatively low dimensionality, capturing text allow better input features to the neural model. However, there are issues. Most NLP models have a fixed size vocabulary that is expensive to modify and expand. Unknown words are treated as out of vocabulary, also known as OOV. Therefore, when new words and concepts arise, the models are unable to deal with this concept effectively. This OOV issue has been a topic of great interest in the field, as shown by the three studies in 2019, which involved federated learning, 2020, which involved graph convolutional network, and in 2021, where meta-learning was attempted to solve this problem of OOV. This is concerning and of great interest because in order for an NLP model to do well, it must be able to understand human concepts. And there are always new human concepts and phenomena such as recently COVID-19, Pfizer, etc. And humans also come up with new terms, acronym, and entities such as work from home, home-based learning, and so on. In order to serve humans well, the NLP application must be able to understand these terms well. It is also of practical importance that we can update the NLP model to learn concepts in specific domains. For example, a chatbot serving the Ministry of Culture, Communication and Youth should know what is community care, what is early childhood development agency, and so on, the domain-specific concept that is related to MCCY. So, how can we deal with unknown words? We will now be reviewing existing approaches that tackle this issue. Let me recap on the motivation. For a given unknown word, we want to give it a representation that the model can understand. In academia, there are more novel approaches involving knowledge graph, federated learning, and meta-learning, but the industry tends to focus more on subword embeddings, which will be explained in the slide below. So what is subword embeddings? In subword embeddings, we decompose an unknown word into meaningful subword. For example, beautifully is broken down into beauty, full, and ly. And the popular method of doing so include byte pair encoding, also known as BPE, and sentence piece. There have been many studies that focus on the efficacy of BPE in handling unknown words. So this approach is good for morphologically related words, but is bad for other unknown words. Now let's move on to other novel approaches. One of the most popular approaches is knowledge graph, which is introduced by Robin Spear and Joe Sachin, ConceptNet 5.5, which use open source knowledge graph to derive new embedding for unknown words. So this is the approach. They use structured data from ConceptNet 5.4, Edges, and PPDB, which is a paraphrase database. These form the structured part of the framework. Also, for the distributional semantic, they use a combination of GloVe 1.2 and Word2Vec Google News SGNS. So how do we combine the structured data in the knowledge graph and the unstructured data gathered from the distributional semantics of the embeddings? The paper introduced this method called expanded retrofitting that combine these unstructured data and structured data together to form the synthetic ConceptNet vector ensemble. The details of this retrofitting is out of scope for the presentation, but you can always check on the link below. So what are the advantages and disadvantages to this approach? As you can see, because it uses structured data, it's very high in interpretability. However, it's super complex to implement in most practical settings. Now let's move on to a second approach involving recursive neural network. This was introduced by Tang Leung, Socher, and Christopher Manning. The recursive neural network, or RNN, not to be confused with the recurrent neural network, build representation for morphologically complex words from their morpheme. This architecture is also known as morpho-INN. So this is the workflow of morpho-INN, and let's pay closer attention to part A, where given an unknown word such as unfortunately, we'll recursively construct the word embedding for this word by first breaking it down to its component and then recursively form the embedding of, let's just say, unfortunate using unfortunate, and then unfortunately from unfortunate and ly. The equation is shown in the box in the slide. Is basically using the concatenation of two embedding multiplied by a weight matrix n plus the bias vector, which will then be fed through an activation layer. For part B is a neural language model that is used to score the n-gram probability, which we will not be explaining in. So recursive neural network provide a systematic way of estimating rare words, but context sensitivity is not done in the morpho-INN itself, and it has to rely on the neural language model above it. So it does solve a certain problem, but it left many unsolved, which inspires to propose our own approach to deal with OOV. So we know that deep-gram vectors exhibit linear additive compositionality, meaning that in their latent space of embedding, there is a compositionality function that can help us derive the meaning of a new word from existing words. And we know that words are defined by their neighbors in the word-to-vec paradigm. So we propose to use a neural network to compose the new meaning of a word using its neighboring words. The objective of the approach is that for a given unknown word, we synthesize a word embedding that is semantically similar. This is important because it can yield a better representation for a given word for different NLP models. And we can use a feed-forward neural network that input context word embeddings and output the target word embeddings. So now let's talk about the system design. In order to design such a synthetic embedding generation system, we need to walk through the implementation of the training and generation pipeline, also discussing the architectural choices of what embedding to use, what data corpus to use, and what network architecture to use. Let's first talk about the training design. For a given unknown word, we can define the target words that are semantically similar to this unknown word. We can then gather the context words from existing corpus and train the neural network in a word-to-vec manner. For the generation phase, we'll then gather context word from online corpus and use our trained model to synthesize the synthetic embedding for this given unknown word from the context word that we gather from online sources. So the first design decision that we need to make is that what embedding should we use for our network? In our approach, we want our embedding to be parameterized because we want it to adapt to any downstream NLP, which can come in BERT, GloVe, or any variants. For this experiment, Glove 100 was chosen for its ease of implementation, and we'll extend it later to Roberta. Why was Glove 100 chosen? Because it was easy to use, and as remarked by Abigail C. in the Stanford NLP Master Course CF244N, that it is largely useful for most practical cases. For the data corpus, the chosen corpus are Wikitext and GigaWord. This was inspired by the fact that Glove was trained on these two corpora, and also remarked by Christopher Manning that Wikitext is very suitable for word-to-vec training due to its content having a lot of explanation of words. So for the network architecture, the model will have the following specification. It input n times embed size, where n is the number of neighboring words and embedding size is the parameterized embedding of choice, and it has to output the same embedding size of the vector. Therefore, for this kind of architecture, we can use the 1D convolution neural network or 1D CNN or feed-forward neural network FFNN. For this project, FFNN was chosen. So let me walk you through the training pipeline. Given an unknown word, we gather and define target training words that are semantically similar to this word, and we take a training corpus. In this case, can be Wikitext, GigaWord, and Common Crawl. We flip through this corpus to gather our training corpus in the form of target word followed by their context word. The model will take in embedding, and in this case, it can be glove, bird, or roberta, and it will also have different architecture, but in our case, we experimented with feed-forward neural network. It will then, once we train this model, we'll yield a fine-tuned synthesis model, which will be used for the deployment pipeline, where we will gather inference corpus from online sources. It can come from web crawler, which crawl internet data, or it can be manually curated. Once we train this, we gather this corpus, we'll feed this into our fine-tuned synthesis model to generate the synthetic embedding, which will then be incorporated into downstream tasks. So here are our training parameters. The architecture is fully connected. We have two layers, and the input and output dimension are parameterized to suit the need of downstream NLP application. The context length was chosen to be 10. We use stochastic gradient descent as an optimizer with learning rate of 0.005, batch size of 64, and 50 epoch of training. The framework used for this project is follow. For the code portion, we designed the whole framework in PyTorch for its ease of customizability. For data warehousing, as Wikitext and GigaWord are not too big, we can use a local hosting service to host our data. And we use the weight and biases monitoring framework to monitor our experience efficiently. Let's go on to the experiment result. We achieved good training result on the cosine similarity score between the trained word, which is in this case vaccine, the golden label, and the synthetic embedding of the word vaccine, sick, poison, and pneumonia. So these are known words, but then we want to compare the synthetic embedding cosine similarity with this golden label per se, and also the loss. Loss in this case is L1 loss, which measures the difference between a vector and another vector. Similarly, we have achieved good result on validation set for Roberta as well. But more importantly, we want to know whether our model can perform on actual, more meaningful words that the model does not know. So we feed this through the COVID-19 and Pfizer, which provide a synthetic embedding that is similar to disease, illnesses, infection, virus, and cancer. And for Pfizer, it identified that this embedding is related to vaccines, vaccination, polio, and flu. Our approach is highly efficient as the data pre-processing takes only 1 hour on Wikitext and 2 hours on GigaWord. Training time takes an average of 15 minutes per experiment with hyperparameter as specified earlier. This has high practicality in a production setting because, first of all, it's lightweight. All experiments can run on a personal computer. It's extensible as our embedding size is parameterized, and it's fast as the whole training pipeline takes less than a day. However, it is not without limitations. There are certain assumptions that we make. We assume that existing corpus has sufficient training data for the unknown word that we want to synthesize an embedding for. Also assume that training target was limited and it has to be manually specified. And our current model lacked the cross-lingual capability. Now let me talk about how we can use this synthetic embedding in an actual setting. Let's just say Roberta. So let me give you an overview of what Roberta architecture is. So Roberta is the robustly optimized bird, and it is a form of transformer which uses self-attention as a form of representation, and the attention formula in this case is a scaled dot product attention. It has the encoder on the left and the decoder on the right, whose layer composed of multi-headed attention. So when we talk about Roberta embedding, people often mean the output of the encoder, which in this case will be dependent on the context query that we feed into the model. This is highly variable and may not be a suitable candidate for our embedding of choice. Hence, we go with the input and output embedding layer, which is shown here. We will be focusing on these two layers as input, and we'll try to generate a synthetic embedding that will go into these layers as well. This will form the input to the architecture model, which will then help with Roberta. So let's assume that we do have a synthetic embedding of a certain word, let's just say COVID-19. How do we actually modify Roberta to take in this synthetic embedding? We will first store a copy of the embedding weight, the existing embedding weights. We'll then add this new word into the tokenizer and resize the embedding layer. We'll override the embedding weights with the concatenation of existing weight and synthetic embedding. We'll then save the new model. So in PyTorch, the structure follow. We first have a synthetic embedding. We'll then take the existing embedding and detach it, and then concatenate it with the synthetic embedding of choice. In order to modify, we must first modify the tokenizer and then resize the embedding layer to this new tokenizer. And finally, overwriting the embedding weights with our own concatenation earlier. So as you can see, it only takes about 4 lines of code to integrate our synthetic embedding into this existing Roberta model. Now let me talk about the future work in conclusion. In summary, we have created a lightweight framework to synthesize embedding for unknown words. We also demonstrate the capability in a proof of concept scope. For future work, we can definitely improve the data selection process and data volume. We also explore the cross-lingual property of the synthetic embeddings. Throughout this project, I have learned a lot and have a lot of takeaways from this project. First of all, I have identified and scoped a problem that is affecting a lot of NLP application in production. And among the different NLP model doing NER, chatbot, and so on, we identified that unknown word was the main cause of concern, and addressing it effectively would be one major improvement to all existing pipeline. We will then hypothesize and brainstorm the solution to that problem while exploring the various candidates for each aspect of the solution framework and select the most viable option. I then learn how to create a minimum viable product for that solution. And that's all for my presentation. Thank you.